This conference will now be recorded.
And I'm going to share my screen. So you should be able to see the review packet. I guess we'll focus on the review packet itself. We had an after-school review session where I did kind of just a general review of topics. I did post, by this time last year, I was using better software for recording these sessions. So the 2018 online review for this particular unit test is also posted under the kind of review section of Unit 6. So if you really feel like you need a lot, if you have a lot of questions or need a lot of help with review and preparation, check that out as well. Again, for those of you who are present, which for now is about 6 of you, queue your questions in the message box there. Corinne is asking a question about the online quiz, which closed at 8 o'clock tonight. So it's a question about two strings placed in a vacuum, and it's about energy transfer. So I'm going to open up the quiz, and while I search for it, you guys can continue to queue questions if you have them. So, Corinne, I'm going to switch the screen that I'm sharing and share my Chrome browser window. Unfortunately, because I scramble the questions, we can't all refer to the same question. So I'm looking for some sort of a question about strings in a vacuum, two strings in a vacuum. Corinne, do you remember what part it was in, A, B, or C? Let's see here. So is it 35, the one that's on question 35 here for me, that shows two strings? There are different materials and lengths, which are different sizes. String 1 is plucked. Okay, there we go. Okay, so string 1 is plucked so that it vibrates in the pattern shown. And very soon after 1 is plucked, string 2, a short distance away, vibrates in the pattern shown. Guitars are placed in a sealed chamber and then air is pumped out of the chamber. Okay. String 1 is again plucked and vibrates in the pattern shown. Does string 2 vibrate? Okay, so this is a tricky question. And it's based on the idea that energy from one of the strings would be transferred through the air. So imagine if I were to draw some of these particles in here. When the upper string hits those particles acquire kinetic energy. They move, and there's a series of collisions. There might be another particle underneath the first one that moves, and it gets hit. That elastic collision transfers energy from one place to another place. We call that kind of a wave a longitudinal wave. There are some other questions about longitudinal or sound waves. Eventually, that particle can collide with this string and get it to move, and we call that there are a few different ways to kind of describe this phenomena, but we could say that it's a sympathetic vibration. I remember when I was cranking music for the Rubens tube, there would be certain frequencies that would get played that would cause the wash tub base that usually is sitting in the corner to start vibrating. There are certain resonant frequencies that will also vibrate at that frequency. And so what this illustrates is that sound is transferred through the air from one string to the other string. And the important piece here is that air is required for that transfer of energy from one string to the other string. And so in this particular case, if we evacuate the air in between the strings, then this transfer of energy cannot occur, and string number 2 will not sympathetically vibrate. It won't get any energy from string 1. So Corinne, hopefully that answers your question. Certainly not something that we discreetly went over, but this question is about energy transfer through the air. So let's take a look at Alyssa is asking question number 22 on the review packet, so I'm going to switch my screen to that. We do this and go back to the review packet and bring up question number 22. So this question shows some standing wave patterns. This came up in the review session after school today. The sketches that are given are representing sound waves, both in open and closed tube pipes, but it's the sketches are of the displacement within the pipe. So normally, if I were to draw an open tube resonator, a tube that's open on the top and on the bottom, usually I draw them horizontally, but in this case, they're sketched vertically. And if I were to do that, and I were to kind of draw an equilibrium position here, and so any variation from that equilibrium position, by the way, we're going to call this, pressure 0. So this axis is pressure. I'm going to have a pressure node at the ends. I have to have a pressure node at the ends. And at the second harmonic frequency, I'm going to get a shape that looks like this, where I get one complete wave fitting inside the tube. Now I can draw the reflection if I want. And we kind of can acknowledge that each one of these loops, this is a half wavelength, the one that I've kind of shaded in and labeled number 1, and number 2 are each a half wavelength. So if this is L, the length of the tube, then at this particular frequency, I could say that L is equal to lambda. They're the same. What's sketched though, if you look over here at what's called open subscript X, it looks fundamentally different. We have antinodes, not nodes at the end. So you can see here that we have an antinode. We have a node here, another antinode, node here, and an antinode. So what's been sketched is like the reciprocal, or if we were to like flip this around. So this is a sketch of displacement. So I'm drawing this, that's 1/2 of one wave. If we just look at this red one here and we ignore the other part of that, I'll draw it in eventually. But that's just 1/2 of one wave. And so we could say then that the length of the tube L is equal to 1/2 the wavelength. This is true for an open tube at the fundamental frequency F1. And so all you need to know is that, where the pressure is the least, which is going to be over here at the ends, that's where the displacement is the greatest. So anyway, the point that I'm trying to make here is that even though we're given a sketch, these patterns look a little different than the pressure distributions that we saw in open and closed tubes in class. These are the displacement sketches, but like, don't let that like mess with you. Here's another way to do it. Let's take a look at OY. I'll do that in a different color. All we have to do is count up the total number of loops. That's one loop. That's 2 loops. This is half of a loop. So this is 0.5 and this is 0.5. So the total number of half loops is 3. So I could say that the length of the tube is equal to 3/2 lambda. It's a wave and a half. And so therefore we know that this one is the third harmonic frequency. O subscript y, or open subscript y, is the third harmonic frequency, and the length of the tube is equal to 3/2 the wavelength. Okay, so I can kind of keep playing this game. It gets a little like long, but let's just kind of blast through it. Let's take a look at the closed tubes here. You guys should be getting ahead of me now. The first one, we can see that the length L is equal to 1/4 lambda, because I'm only looking at 1/4 of a wave. CY, L is equal to 3/4 of a wave, because I'm looking at, if I just look at one of these, that's 3/4 of a wave. The last piece of the wave would be that. And then finally, we get one complete wave plus another quarter of a wave. So C subscript Z is 5/4 lambda. This is the fifth harmonic frequency, and C subscript Y is the third harmonic frequency, and this is the first harmonic frequency. Remember that for a closed tube resonator, there are no even integers harmonic, no even integer harmonics, only odds. So question number 2 is saying, which organ pipe shows a standing wave which has twice the frequency of one of the other waves shown? So when I look over here, F1 for O subscript X, this is F1. F3 is going to be 3 times the frequency. Here's another way that I can do it. I can say V is equal to F lambda, and therefore I'm solving this for F. I'm going to get V over lambda is equal to frequency. V is a constant, so it's not changing. It's the speed of sound, and in all of these instances, the speed of sound is 343 meters per second. So now I can say V is proportional to 1 over lambda. And in all of these cases, I can say frequency is proportional to 1 over, and so for, let's say, OY, I can say lambda is equal to L. So the frequency is equal to 1 over L. So let's kind of do this. I'm going to do this in a different color for each one of these. Let me find a color I haven't used. Let's use orange. So for OY, we can say that frequency F is equal to 1 over L. For O subscript X, we can see that frequency is equal to 1 over 2L. So keep, now wait a second, I made a mistake. This is not correlated with OY. I kind of just drew this randomly over here. So that is not one of the 5 tubes. So I need to kind of redo this one here. Frequency is equal to 1 over 2/3 L. So make sure that you catch that, right? Because I can rewrite this. If I solve this for lambda, I'm going to multiply both sides by 2/3. That becomes 2/3 L is equal to lambda. And that's what I'm basically substituting down here in the denominator. So F is equal to 1 over 2/3 L. Another way to write that, if I wanted to, is F is equal to 3 over 2L. So anyway, we can see that the frequency of O subscript X is 1/3 the frequency of O subscript Y. So we're not done. We're going to just kind of keep going through this. And so I get frequency is equal to or proportional to 1 over lambda. And in this case, I'm going to say it's 1 over 4/5 L. This one is frequency is equal to 1 over 3/4 L. And then finally, I get frequency is equal to 1 over 1 over 4L. So we can see in this case that C subscript X, the frequency is 1 over 4L. And we can see that O subscript y is twice, bear with me here for a second, twice the frequency of one of the other waves. So now I have to basically compare all of these. I think I'm going to rewrite this as F is equal to 5 over 4L, F is equal to 4 over 3L, and F is equal to 1 over 4L. So the answer key is showing DOY, which is open Y, and we have to say that that is twice the frequency of one of the other waves shown. Bear with me for 1 sec. So if L is equal to 1, this is 3/2. And this one is F is equal to 1/2. So 3/2 is twice the frequency of what? 3/2, so that's 1.5. So one of the other ones needs, in order for that to work out, would need to be, which pipe organ shows a wave with twice the frequency of one of the others? Still not seeing it. Corinne's saying it's twice the frequency of CY, which is 4/3 L. 4/3 is 1.3 though, and I don't see that being twice. OY is 1.5. Three halves. Let's take a look. Here's another. I think this is probably the best way of doing it. If you look back at the if we look at OY, there are 3 half waves. Let's just call it 3 total loops. So we've already kind of gone through that. And then in CY, there are 1.5 total loops. So here's one, and here's the other half loop. So we basically get a total of 1.5 loops. So here's the full, here's a loop, and here's a half loop. And the other one has 1, 2, 3. Since V is equal to F lambda and V isn't changing, then we can see that OY has to have twice the frequency of CY. So I can see that now. I think that was a much easier way of doing it than solving for F. So sorry that I kind of went around that long route to kind of answering question number 22. All right, yeah, and that's what Corinne is saying as well about counting wavelengths. Let's take a look at review packet, one of the FRQs, and it looks like part B on FRQ 2. So let me get rid of this stuff. So the FRQ number 2 shows this mass that falls and lands and hits a spring. And if we were to draw like a free body diagram for, question for part B, if we were to draw a free body diagram when the spring reaches the equilibrium position, we would see that the weight would have to be equal to the spring force. And so that's what basically is written here, where F sub R means the restoring force of the spring. We could, vis-a-vis Hooke's law, say Kx, F of the spring is equal to Kx is equal to mg. And so that's what they're asking. What is the spring force at equilibrium? It's equal to the weight of the block. And so we get 19.6 newtons. We just multiply the mass times the acceleration due to gravity. Corinne, make sure that I've answered your question, and I'll take more questions in the kind of chat. Part D, asking about spring constant on the online quiz, is Jess's question. So I'm going to flip screens to the online quiz. So Jess is saying there's a question in part D. Oh, sorry. And then Ryan is also asking a question about something in part B that starts with a 512 hertz wave. So let me answer Jess's question first, and then I'll do Ryan's. We're going to go over part D, and it asks to find the spring constant. So Jess, let's get to part D, and let's see if we can find it. I think it's that one, number 40, at least on mine. So yeah, the figure shows a pole with a spring around it and a 1 kilogram block with a hole in the middle on the top of the spring. A light horizontal string is attached to the block in the wall. When the block is oscillating at 5 hertz, the standing wave shown is formed. So this question, they gave us the frequency of the spring mass oscillator. In order to answer this question, it's important for you to identify this thing, which is bouncing up and down, is a spring mass oscillator. And so we're given the frequency as 5 hertz. So we know the period is 1/5 or 0.2 seconds. So I can write period is equal to 2 pi root m over k. That formula is given to me in 2 pi root m over k is given to me on my yellow equation sheet, and they give me the mass of the block. And so I kind of have everything I need. I have the period, 2 pi is a constant. I'm looking for k, and the mass is given. So I'm going to divide both sides by 2 pi. That becomes period over 2 pi is equal to root m over k. And the kind of next step that I would take is I'd square both sides. I get period squared over 4 pi squared is equal to m over k. And now I can kind of cross multiply and solve for k. So this would be, I could just flip both sides. So this is going to be 4 pi squared over period squared is equal to k over m, and then I'll multiply both sides by m. And so I kind of have everything I need to solve for k. Jess, make sure that I've answered your question and you're satisfied with that for question number 40. Ryan asked one in part B that starts with a 512 hertz sound wave. So let's go up here to part B. I think it's question number 13 for me. And so we can see that it's here. 512 hertz sound wave travels 100 meters, and they want to know the wavelength of the sound wave. For starters, the distance that this thing travels has nothing to do with the wavelength. We're given the frequency. Yikes, my pen won't write. We're given the frequency, and we know the speed. The speed of sound in air is 343 meters per second. This problem, potentially uses 340 meters per second, but even if they used 331 meters per second, any of those variants of the speed of sound, by the way, that lower one is the speed of sound at 0 degrees Celsius, and the upper one is the speed of sound at 20 degrees Celsius, and the middle one is just kind of this, approximation, since these numbers are so close. So we're just going to say that V is equal to F lambda. And then we're just going to solve it for lambda. It's going to be V over F is equal to lambda. And so we're going to, I'm going to just say, I'll just use 340, and we'll divide that by the frequency of 512 hertz. And it looks like it's about 3/5. So I would need a calculator. So I'm guessing that 2, just by 3/5. Answer number 2 would be the kind of best answer. Ryan, make sure that I've answered your question for that particular one. Corinne asks a question about gravitational potential energy and the conservation of energy equation. I've seen these types of questions before. So this is getting back to the review packet. I think it was the same question in FRQ number 2. And the thinking is that the gravitational potential energy component is so small that it can be ignored. There's also, in this type of a problem, it actually would behave identically if the system were a traditional spring mass system on its side. So if I had some sort of spring mass oscillator on a frictionless surface vibrating back and forth this way, that's the same thing that's going to happen when this 2 kilogram block reaches its equilibrium position. Let's say for a second that it's not moving, and then somebody comes along and pushes it down to this kind of lower position. It's going to vibrate up and down between A and negative A. So the gravitational potential energy piece is taken into account when the spring does some work as the block gets lowered to the equilibrium position. So the 2 kilograms with the 200 Newton per meter spring constant are going to vibrate with the same period and frequency as if I had placed it on its side. So that's kind of one approach to thinking about the gravitational potential energy in FRQ number 2. The other approach is that the amplitude is so small relative to the energy stored in the spring and the kinetic energy in the system that if you were to factor it in, it's not going to sufficiently change your answers. So there's a couple of different approaches to that, but hopefully, Corinne, that answers your question. But I think I would focus more on the idea that once the block reaches that equilibrium position, and we're calling that 0, even though the kind of up and down elements are adding and taking away gravitational potential energy, they're trivial when compared to the other elements. So I'll just kind of like leave that where it is and field any other questions on either the online quiz or the review packet. JT is asking about part D on FRQ number 3. So let's take a look at that one. So in this one, this kind of whole setup should look familiar to, with the exception of the use of a tuning fork. I have had students who are like, what the heck is a tuning fork? And so a tuning fork, if you were to like hit this side here with typically some sort of mallet or a hammer, it's going to cause the tuning fork, the kind of fork end, to vibrate. If you know what this, if you've seen a tuning fork before, then then obviously this is trivial. But a lot of students actually haven't. They used to be used for, let's say, like tuning instruments, because the vibrational frequency of this particular fork would be a function of the length of the fork and the thickness of the material, and so they would effectively build them to have a very specific frequency. So perhaps the frequency of this particular tuning fork would be 512 hertz or 440 hertz, but that's really what a tuning fork does. And so it's just the source of vibration in this problem. We've done a lab like this with the table pulley on the end here and the mass providing the tension, and we need to know something about the linear density. You guys might remember measuring the sample string in that lab. The only difference between this kind of experimental setup and what we did is that we had effectively an electromagnet, or just a speaker with a kind of a wine cork in it, and it was attached to the string. So that was really the only difference between this setup and what we've already done in class. So part D is asking, and I would consider this kind of a very important kind of aspect. If a point on the string at an antinode moves a total vertical distance of 4 centimeters. So you can see that I kind of come back to it in a second. So it moves a total 4 centimeters. They want to know what the amplitude of the wave is. So if I go and I pick some antinode point, let's choose this point right here. So there's the red dot. It's going to go all the way down to the bottom, which is 2 amplitudes, right? Amplitude is just this distance from the maximum displacement from equilibrium. We call that the amplitude. Now, going from all the way to the top to all the way at the bottom is 2a, but then it's got to go all the way back up to where it started from. That, by definition, is how we describe one complete cycle. If I were to sketch that larger so that we could see it, then we would say, hey, let's take a look at this blue dot right here. It's going to go all the way down to the other side and then all the way back. So that's going to be 4 times the amplitude. So this would be 1 centimeter, that would be 1 centimeter. So it's going to be 2 centimeters just to get to the other side, and then another 2 centimeters to get back up where it started from. And so therefore, our answer to part D of FRQ number 3 involves recognizing that the amplitude then is just 1 centimeter in this case. So make sure, Jess, that I've answered your question to FRQ 3 part D. Ryan is asking a question about the yellow equation sheet, and I would say that if I'm just going to be blunt about it, the 2 equations you need to know are simply the speed of a wave on a string. This is easily going to be the most important one. The only equation on the test, I don't know why it's not on the yellow equation sheet, but I can certify that I've seen AP Physics 1 questions that would require you to kind of know something about it or know it in its entirety. So for starters, the one that I've written here in blue and put an asterisk next to is something that you should know, where F sub T is the tension in the string in newtons, in units of newtons, and mu is what's called the linear density. Linear density is the mass per unit length, and so therefore the units would be kilograms per meter. So there's kind of V string. You should also know something about the speed of sound in air. So, for starters, you could just, remember 340 meters per second. You could additionally say that the speed of sound has a temperature correction formula of 331 meters per second plus 0.6 T. I would say the one that I've just boxed in here, this kind of temperature corrected formula for sound, is probably less critical than the one that I put an asterisk next to for the speed of waves and strings. Excuse me. So these two pieces here that I've kind of boxed in would be the only two equations in the entire course that you need to kind of commit to memory. The upper one being more important, because you could get away with just memorizing, hey, 340 meters per second, or you could program that into your calculator. You're permitted to bring in a graphing calculator that has memory. You are not required to clear your memory before the test. And when I say the test, I mean not only the test on Unit 6 in our class at WHS, but also the exam in May. So that's legit. That's considered something that you can do, and I certainly think it's reasonable, along with quad solve. I don't think it's a bad idea to put in there. Okay, so so hopefully I have answered your question about the equations that you need to know, Ryan. Marika asked a question about practice problem involving waves either on a string or on a tube. I think that's a great place to kind of finish. Corinne asks a question about why acceleration is a maximum at X max. If I go back, actually I kind of erased that. So let me just kind of sketch in some kind of random spot here. If I have a spring mass system and I just kind of draw in a really quick one here, so, and it's sliding on a frictionless surface, we'll say that this is the constant K. If I draw a vertical line here and I call that the equilibrium position, let's call that position 0, then when I come over and I pull it to the left to our maximum displacement to the left here, we're moving in the negative direction, and so we're going to call that negative A. If I were to have made like a free body diagram of the block there, of course, there's a normal force going up and a weight force going down, but the spring force is acting to the right at that point. And so when I'm displaced the maximum amount to the left, I have the largest spring force to the right. Let's remember that the spring force is a function of K, which is just the elastic constant. It's a number that doesn't change, multiplied by X, where X is how far you are away from the equilibrium position. So as X becomes a larger number, the spring force becomes a larger number. And so therefore, when I reach my maximum displacement to the left, I get the largest restoring force, or the spring force, to the right. And we could say that that's equal to our leftover force, our net force, which you can write as MA. So really, this becomes KX is equal to MA. Solving it for A, I get KX over M is equal to A. And so therefore, we can see that acceleration is dependent on three things, and only one of them is changing. K is a constant, M is a constant, X is the only thing that's changing. And so when X is a maximum to the left, A is a maximum to the right. Riley asked about types of questions we'll see and how to approach each. So I guess, just to kind of rehash this, and then I'll finish because we have about 20 minutes left. So I'll kind of answer this question, and then I'm going to answer Marika's question, which was, can we do like a practice problem? So let me bring up a blank sheet of paper. Give me 1 second here. I'm sure there's a smarter way to do this, but I'm going to just open up a blank document in Word so I kind of have some white space. There's got to be a smarter way, but anyway, that's what we'll do. So kind of just a rehash in short order, kind of our kind of review session after school. We talked about a pendulum, 2 pi root L over G. You'll see pendulum questions. Keep in mind that this pendulum equation is valid for fairly small angles here. Typically, when theta is less than 15 degrees, we kind of accept period is equal to 2 pi root L over G. And then this starts to break down. It doesn't work as well at larger angles. But 15 degrees is usually considered that threshold. Keep in mind that there are also some fair game kind of energy questions. So if we knew what the height difference is between those two dashed lines, let's call that H, then we could answer questions about how fast we were going at the lower position. That's just conservation of mechanical energy kind of rehashed. But that's the pendulum. Notice that the pendulum period and frequency are independent of the mass of the pendulum, and also probably most importantly independent of amplitude. There's no accommodation for either mass or amplitude in that formula. Then there's the spring mass system. We've seen a lot of that tonight. 2 pi root m over k. Both of these, by the way, are given to you. There's a ton of stuff on spring mass systems where a mass is vibrating to the left and to the right. It's very common to see kind of graphical outputs associated with a spring mass system. So there might be like a position versus time graph. And if we, you got to pay attention to this stuff. If we start by pushing it over to the left, that would give us a starting position of negative A, which means that our position versus time graph would start at negative A, and we'd get this kind of negative cosine function. And if we take the first derivative of that, for those of you in calculus, or we just take slopes of tangent lines, we would see that if we release it from negative A, the velocity is initially going to be 0, but then it's going to be positive. So we're going to get something that looks like that, positive sign. So this x is negative cosine, and we can see that velocity then is positive sine. And then lastly, we can mess around with acceleration and see that acceleration then is a maximum when we're at negative A. It's a maximum positive. We just kind of went over this. So that's going to be acceleration being cosine function. So you'll see these kind of graphical questions. If you're asked about speed, it's typically conservation of mechanical energy. So as we saw with the pendulum, we could say that the energy at some position is equal to the energy at some other position. And if it's an acceleration question, again, as we've seen tonight, it's a dynamics question. Spring force is equal to net force. So we get kx is equal to ma. Solve it for a. We get kx over m is equal to a. So these are just kind of common outputs from velocity or acceleration. And, in short, that is the difference between a pendulum and a spring mass oscillator. There are also, all sorts of questions on open and closed tube resonators and strings. You guys should know, if I just kind of quickly go over that, that would be the standing wave for the fundamental frequency. And this would be the kind of second harmonic frequency. That's F1, F2. And in the same length, then now we have F3, which is going to be 3/2 of a wavelength. Those are for strings or for open tube resonators. That tends to change when we have one end that's closed. We call those closed tube resonators. And what we're going to graph on this closed tube resonator is the distribution of pressure inside the tube. Remember, and we kind of focused on this both in class and in that review session, this is not what the wave looks like, but it's a graphical distribution of pressure, with this being high pressure, I'll call that P subscript H, and then this being low pressure, or a pressure node at the open end. And so at the fundamental frequency for a closed tube resonator, we see then that L is equal to 1/4 lambda. So, there's all sorts of patterns. The next harmonic, of course, is L is equal to 3/4 lambda, et cetera, et cetera. So, all of these different strings, open and closed tube resonators, kind of work carefully with V equals F lambda and some of the speed equations. And so I think I'll answer, Marika's question last, which is, hey, let's do something in this area here where we have to kind of use that stuff. So I'm going to expect you guys to not just follow along, but maybe kind of work on this a little bit off to the side. You can break out a calculator if you'd like while I kind of set something up. So we're going to say that we have a closed tube resonator. One end of the resonator is open. Maybe it's a clarinet. And this is going to be the closed end, the reeded end of the clarinet. There are some valves here that would kind of change things. But for now, let's just take a look at this thing and say that if this is the open end, question number one is for this closed tube resonator to draw a pressure distribution graph. Pressure distribution at the fifth harmonic frequency. Question number two is going to be if the length of the tube, so let's go ahead and make sure that we define that. There are no surprises here. If the length of this clarinet, and I'm kind of making this up as I go along, if L is equal to 80 centimeters, let's make that a bunch of sig figs here, 3 sig figs. If L is equal to 80 centimeters, find this fifth harmonic frequency. Like, what is the fifth harmonic frequency? And let's start with those two questions and see where that takes us. So go ahead and I'll give you guys a minute or two head start, and then at least start by making a sketch of the fifth harmonic frequency, and then go from there. Not my best work, but close enough. So at the fifth harmonic frequency, which we should see then that L is equal to 5/4 lambda. In other words, we have, here's 1/2 of a wave. Here's another half of a wave. So the shaded region right there is one complete wave. Hopefully you guys will remember when we had standing waves on strings and we hit that with a strobe light. And then we have finally 1/4 of a wave. So we can say then that 4/5 the length of the tube is equal to 1 wavelength. Then, so there's the answer to part one, drawing the pressure distribution at the fifth harmonic frequency. Question number two then will be answered by using the speed equation. V equals F lambda. Well, we're going to make that substitution in for lambda. So this becomes V over lambda is equal to F. And at the fifth harmonic frequency, this is going to be V over 4/5 L is equal to F5. Now, another way for me to write that is 5V over 4L is equal to the fifth harmonic frequency. And now I can just kind of substitute some numbers in. It's going to be 5 times 343 meters per second. We can see that I used the number 343 for 20 degrees Celsius, but you'd get a very similar answer if you use 340 meters per second. I'm going to divide it by 4 times the length of the tube, which I have to make sure that I'm in meters so I don't have unit mismatch in my numerator and denominator. So I get 5 times 343 divided by 4 times 0.8. And I will need to grab a calculator in order to do that expediently, I'll let you guys get ahead of me there. I'm getting about 536 hertz. I'd probably have to deal with some sig figs here, although the only input numbers that I'm using are 80 centimeters, which was 3 sig figs, and 343. So I think I'm good with 3 sig figs there. Did anybody else get 536 for the fifth harmonic? Good. All right. So let's finish there. If you do have questions beyond this, feel free to check out the other 2018 review session. You can also see me before school tomorrow or during 1A. I'm in F310. Marek, I'm so happy that you asked me this question because I think for the record, you have asked this question on most of our review sessions. About 20, this is a pretty standard, this is the last full-size summative in the course. So it'll be roughly around 20 multiple choice questions and either 2 or 3 FRQs. I will have the bubble sheet. We're going to be using the optical scanning. So, pretty standard format. The last assessment in the course, which will be on Unit 7, electricity topics like DC circuits, I think I'm going to do a non-paper test. I'm going to do some screening with immediately graded online assessment tools. So we'll see how that goes. But it'll be different both in the format being all electronic and obviously immediately graded, and it'll be fewer questions. I think it'll be more like 10 multiple choice and 1 FRQ for that last test. But obviously that doesn't affect us for tomorrow. So that's it for today. I hope that was helpful in some way. Have a good night, everyone.